Hello, everybody. So today is Tuesday, and you guys have a test on Monday, September 28th. We are covering our last learning target today, odd and even functions. You're going to do great. And let's get into it. Just a few examples. So a function is even if and only if f of negative x equals f of x. So this phrase, if and only if, works both ways, moving left and moving right. So if you know the function is even, then you know that f of negative x equals f of x. Or if you know that f of negative x equals f of x, then the function is even. So this is kind of difficult to kind of grasp immediately, but what this really means is if you replace all the x values with their opposites, the result will be the original y value. So for example, if 3, -7 is on the graph, then so is -3, -7. So 3 resulted in -7. But if I take the opposite of 3, that is -3, then the result is still the same. And that relationship will happen for every ordered pair if the function is even. One of the consequences of that is that it's symmetrical about the y-axis. So here's a real funky looking function, but it is even. I picked out four ordered pairs to show you. -4, 5 is right here. And if I change the x value, -4, to +4, the result is still 5. So -4, 5, and +4, 5. 2, 3 is right here. If I replace the x value 2 with -2, I get the same result, +3, -2, +3. And same thing with -1, 1, -1, 1. But if I change the x value to +1, the result is still 1. Algebraically, you have to replace all the x's with their opposites and show that it's the same function. So here's this function. God knows what this looks like. You got a radical, you're dividing, all sorts of stuff is going on. But I had to show that this is even. So I evaluate f of the opposite of x. So now all the input is going to be this -1x here and here. So -1x to the fourth, -1x squared. Well, -1x to the fourth, that exponent got a little big there, is -1x times itself 4 times. And -1x squared is that times itself 2 times. Well, all these -1s, they cancel out. -1 times -1 is 1. And -1 times -1 is 1. So it all just becomes this +1. So what you end up with is you end up with the exact same function that you started with, which is f of x. So f of -x equals f of x. So this function is even. And if we were to graph it on Desmos, it would be symmetrical on the y-axis. A function is odd as if when you replace all the x's with their opposites, the result is the opposite of the original y value. So for example, 3, -7, if you replace 3 with its opposite, -3, the result will be the opposite of what 3 produced. So 3 produced -7. Well, that means -3 would produce +7. So in other words, both values change. Both x and y change their signs. They become their own opposites. And what that means is it's symmetrical over the origin. So here is another function, and it is symmetrical about the origin. -4, 5 is right here, but if you change the signs of -4 and +5, you would get +4, -5. And there it is on the function. 2, -3 is on the function. And if you change both signs, you would get -2, +3. And that's on the function. Algebraically, what you need to do is replace all the x's with their opposites and then show that it equals the opposite of the function. So I replace all the inputs with -1x. So that's 3 times -1x squared plus 9, all divided by -1x. Well, the -1x squared just becomes x squared because those two -1s cancel out. But not so down here, you're dividing by -1x, so that's just -1x. But this fraction, if you're dividing something by a negative number, the whole fraction becomes negative. And look at this. This is negative 1 times this function, which is the original. So it's negative 1 times f of x. So it is odd. By replacing all the x's with their opposites, you get a negative f of x. These are the most common even functions. The parabola, just x squared. But notice if you move this parabola left or right just a little bit, it won't be even anymore. To be even means it's symmetrical on the y-axis. Cosine of x is symmetrical on the y-axis. It is even, and so is the absolute value function. Extremely common odd functions are y equals x, just the linear function. Notice you've got 5, 5 is on the graph, so is negative 5, negative 5. Y equals x cubed is also a famous odd function, and also sine of x. 3 examples. Is g of x odd, even, or neither? Here's g of x. The way to solve this algebraically is to replace all these x's with their opposites. In other words, the opposite of x. So x squared becomes the opposite of x squared, plus 7x becomes plus 7 times the opposite of x, and minus 1 has nothing to do with x, so it's still minus 1. And then you simplify. The opposite of x squared is just x squared. And 7 times the opposite of x is negative 7x. And minus 1 is still minus 1. So here, this is done. This is simplified. It's not the same. It's not g of x, so it's not even. But is it opposite? Is it the complete opposite of this? And the answer is no. The opposite of g of x would be negative x squared minus 7x plus 1. It would be the complete opposite. So it's not even, it's not odd, therefore it's neither. The g of x, this is an example of a function that is neither even nor odd. And since it's neither even nor is it odd, it's not symmetrical over the y-axis, and it's not symmetrical over the origin. Is this function even, odd, or neither? This looks like a crazy function. Well, replace all the inputs with the opposite of x. So the opposite of x to the 10th power times the square root of the opposite of x to the second minus 9 plus 1. I purposely put this here. If you're tempted to think that this equals x minus 3, you need to correct yourself. This does not equal x minus 3. You're not taking the square root of these two terms. You're taking the square root of the whole difference. Anyway, moving on here. Well, the opposite of x to the 10th power means you've got 10 negative x's. So that's 10 negative 1s. That's an even amount. All those negative 1s cancel out. So you're just left with x to the 10th. And then for the same reason here, the opposite of x squared, that negative 1 cancels out. So what you end up having is this same function as the original. If you replace all the x's with their opposites, you get the original. So that only happens when you've got an even function. And if it's even, it's symmetrical about the y-axis. And lastly, this one. Is this even, odd, or neither? So I got a 5th degree polynomial. I'm going to replace all the inputs with their opposites. So what is the opposite of x to the 5th power? So here you have the opposite of x times the opposite of x times the opposite of x times the opposite of x. One more time. You've got 5 opposite of x's. And those negative 1s in there, these two negative 1s multiply and become positive 1. These two negatives multiply and become positive, but you're always left with that odd man out. I mean, this is odd. You have, when you pair them up, there's always one left over. So the opposite of x to the 5th power is negative. It'll be negative 2 times x to the 5th. Same thing here. 10 times the opposite of x would be minus 10x. Now, this is definitely not the original, but if you factor out a negative 1, you get the original. Factoring out -1, you get 2x to the fifth plus 10. 10x. I forgot my little x there. Hold on. And that is -1 times the original function. So replacing the input with their opposites, you get the opposite of the function. That happens when the function is odd. And if it's odd, it's symmetrical over the origin.